Okay, today I'm trying something new. So let's say that they ask us to design and check um, um, an angle that is carrying a brick veneer, and they also ask us to check an HSS bar sustaining that load. So as you can see from this drawing, the brick veneer has a concentrated load hitting the angle, and then from the angle it creates a couple and it transfers into the beam. So here are our given values. We get an initial testing value of a 3 by 3 by 1/4 angle, an HSS 8 2 by 2. The brick we assume that is a 40 PSF. An angle beams are usually 836 steels. So here what they ask us, check the angle and check the HSS. Now let's start with our first calculations. First we create the load and we convert it into a linear load, 5.5. This is the span, 12 feet, and we get this load. Then from there, what I did, I also converted the steel value and I calculated the effective length. Then step number 2, we converted the PLF into a concentrated load. Here's our concentrated load. After that, we calculated a CX value, the required. So we plug the fracture moment here, pounds per inch, and we calculate the Fy. Here we are. Then from there we go down and we utilize this formula to try to check the thickness of our angle to see if it is good enough. So we go. This is our effective from over here, and we solve for t. We get this value. So we need a value of 0.492 inches for it to be effective. So our 3 by 3 by 1/4, that is 0.25, is not good. So we need to get another one. In this case, a 3 by 3 by 1/2 will be okay because 1/2 is close to 0.492. So what I decided to do, I decided to up it up to a 4 by 4 by 1/2. This will give me a bigger effective. So we calculate again. As you can see, now it went from 9 to 16 over here. Then we solve for t again. And now this value goes down to 0.429. So this should be okay. Now, another quick check that I did for this, I call it quick check because my friend Pete teach me this. F small over F big. This has to be less than 1 for it to check. So F small is equal to M moment over your S. Your F is the one we calculated over here. Your Fy. Then we calculate our S, given our effective of 9. This is for the first angle. And when we go down, we can see that it's not good. All right, 9.5 over S, 104, 104.5 over the 21.6. F small over F big, it's more than 1. It's like 3 or something like that. So now we check our next angle, the 4 by 4. S is equal to 0.66. F is equal to 9/8 over 66, 14.7. 14.7 over 21.6. This is less than 1. So that means that the 4 by 4 times 0.5 will be okay. Now, this load is going to be transferred into the HSS, our concentrated load from over here. So it's here. we do summation of we solve for this force here. We get our fourth one. Now what we do, this is the angle. It's getting stick to the HSS along the whole span. So we take it as a beam, getting a concentrated load. Distributed, sorry, 2,800 pounds against the whole span. What is your maximum moment? This is from the book if you don't know how to do that, but you should know how to get your maximum moments. We get this as our maximum moment. Now we get the moment from the couple, this one and this one. Now this couple is gonna act in the middle, so it won't act directly on the center line of the HSS, but it acts in the corner. So I just assume it was at the center line for easiness. And we get this moment added to the value. So what I did, I added all the moments. So I got a 51.5 keeps fit moment. Now we're gonna check the HSS to see if it's good. We go into the book. We're using ASD, so no increasing factors. We got a 21 keep fit load, so that is way less than the 51.5 needed. So we need to up the HSS. I decided for an HSS 8 by 4 by 0.5. We all get these numbers from the steel code. 53.8 is bigger than 51.5, so your HSS is okay. And if you think that's too close, I decided to went a little bigger just for safety. All right, so that's how you design a steel angle, having a brake veneer mounted on it, and then check for the HSS beam resisting that load.